Hello everybody, and welcome to the next lesson in the Organic Chemistry online series for Chem Complete. And in this lesson we are going to finish up hybridization of carbon, which is what we started in lesson 1, if you were with me there. So in this lesson we're going to be talking about sp2 and sp hybridization. So if you need some help with sp3 or you need to understand hybridization in general, go back and check out the first lesson. And then this is the follow-up to that lesson. This will finish off hybridization. So we're going to pick up with sp2 hybridization. When we deal with sp2 hybridization, hybridization is occurring between one s and two p orbitals. So remember last time we said when we're talking about sp, when we want to classify something as, sp whatever, when we're classifying that particular molecule, the value that gets associated with the p is the number of p orbitals that are recruited in that hybridization process, so to speak. And so when we have sp2 hybridization, we're taking one s and two p's. That's what makes it sp2, okay? This leaves one p orbital behind, because we normally have three p orbitals if we're dealing with carbon, or any of the level 2, well, in fact, you only have three p orbitals for any atom. When you're dealing with that n equals level, for that quantum level, you get three p orbitals. But this leaves one p orbital behind when we're dealing with carbon, and that p orbital is not involved in the hybridizing. So when we have sp2, we take the s, two of the three p's, we create the hybrids, and then the remaining p orbital is left in a unhybridized state. It's just a regular p orbital. And that empty p orbital will very often be used for pi bonding. So you'll find double and triple bonds. The electrons that are making up double and triple bonds, those are hosted in p orbitals that are left behind that are not hybridized. You can find them in d orbitals and stuff like that, but again, in carbon, we do not have access to d orbitals. So we're really only focusing on s and p in organic chemistry. And I just want to mention, it's not the only thing. Sometimes you can leave empty p orbitals behind. You have a plus charge in your 3a elements. You have an empty p charge where an empty p orbital where you can accept electrons like a Lewis acid. But in general, these p orbitals, when we're looking at carbons, for the most part, in organic chemistry, you're going to find pi electrons hanging out there. So this is an sp2 energy diagram, just like we had for the sp3. And if we take a look, again, keep in mind the 1s is off limits. That is not a valence shell anymore since we're in level 2 for carbon. And so the red are hybridized, the blue is unhybridized, and I'm circling what is going to be put into the hybridization here. So these are the hybrid orbitals down here to the right, and I've got 2s, right, and I've got two of my 2p's. The blue one is going to be the unhybridized p orbital I leave behind. So if I do that, this is what I end up with. So go back and look here, total of 4 orbitals and total of 4 electrons, right? So if I move forward, total of 4 orbitals between the p that's left behind and the 3 hybrid orbitals. And then if I take a look at the electrons, right, I've got 3 electrons in the hybrid orbitals, and then I have 1 electron left in the p orbital. And this electron that's left in the p orbital is the electron that will be used in a pi bonding system. Now, this is for one carbon. Anytime we have sigma bonds, like we talked about last time, or pi bonds, we need 2 electrons to make a bond. And so this is for one individual carbon. We'll look at an example where, we're looking at 2 carbons coming together to form this. But you guys should be comfortable with this after the last lesson. All right, so this is, I am by no means an artist, but this is my best representation of an sp2 orbital. Just wait till the sps. They're going to get even messier, okay? But the sp2 orbital, if you take a look here, you've got your hybrid orbitals. This should be trigonal planar, right? So ideally, these would have 120 degrees between each of the reds here when we're looking at the bond angle. So again, if we're taking a look at this, these are the hybrids, right? The red ones here. And then the blue one is the p orbital. Note that the p orbital has its regular dumbbell shape, right? I haven't hybridized that, so I get the above and the below when I'm dealing with this p orbital coming through the carbon. The dots are representing the electrons. Okay, the dots are representing the electrons. And so when I'm dealing with these electrons, I have 4 around the carbon. In this case, 3 of them are in hybrid orbitals because I'm sp2. 1 is left in the p orbital. Okay, so if I take a look at actually bonding two of these carbons together that are sp2 hybridized, this is what it would look like. I've got the overlap of the carbon-carbon single bond. So if I take a look over here, this is ethene, okay, which is a carbon-carbon double bond with some hydrogens. It's probably one of the simplest sp2 bonding examples you could take a look at. And so when I look at this, right, I've got sp2, sp2 for both of these carbons, but let's look at what's happening here. One of these two bonds in the double bond is a sigma bond. I always start with a sigma bond, then I can layer my pi electrons over top of my initial starting bond, my single bond. So I have a sigma bond between the two carbons. I also have sigma bonds between the carbons and the hydrogens. Now note the hydrogens do not have hybrid orbitals, and if you remember from last time, they cannot have hybrid orbitals because they only have an s orbital. You need to have s and p in order to hybridize. So if I take a look at this here, I've got the hydrogens bonded and overlapping with the hybrid orbitals, and the carbon also has a hybrid orbital. But that double bond is a result of pi electrons, and the pi electrons are really being shared between the p orbitals right here. And you can see I sort of drew this bridge that's curving between the blue here and the blue down here. Okay. Now a lot of people get confused. They think this is a triple bond. This is not a triple bond because there's one blue up here and another down here. Okay, this is a double bond. You have to keep in mind orbitals are sort of the home ranges that the electrons can wander about in, right? They're the confinements for those electrons, or the theoretical confinements or boundaries for those electrons. And so it's saying that the pi bond can exist in any of these blue areas. It can basically, imagine that you have the single bond right here, right? And then we've got the pi electrons that are sort of rotating above and below that single bond is the best way to view it. A lot of times you'll see this in books with different little bubble-looking figures, and that's what that's representing. All right, so sp hybridization. This one's going to go a little bit quicker because you should be getting the hang of this. In sp hybridization, when this occurs, we have one s and one p, right? Which means I leave two p orbitals behind. So I continue to leave more and more p orbitals behind when they are not being involved in hybridization. And the empty p orbitals, again, will often be used in hosting double and triple bonds. And you can host double bonds while you're sp hybridized if you have double bonds on each side of the carbon. And we'll take a look at that with carbon dioxide at the end of this lecture. So here's the sp diagram. Should be very familiar. Again, one s is off limits. Here's 2s and 2p. The two reds, I'm picking out an s and a p, which is what makes this sp hybridized. And I leave two p's behind that are unhybridized. That means I have two electrons, right, in the pi bonding orbitals. I have two in my hybrid orbitals. Now here, again, to the best of my ability, is an example of an sp orbital. Now keep in mind, p orbitals have three directions, px, py, and pz. So you have your hybrid orbitals, which are linear, and sp molecules would have linear molecular geometry. So you can see the red is making sort of a straight line through the carbon there. And then I have a p orbital. In this case, it looks like py going up and down. And then you have another p orbital, which I'm representing here as pz. Now keep in mind, pz is a little difficult to represent when you're drawing it out. It would really be coming in and out of, when I'm in class, I say the plane of the board, but the plane of the computer screen, right? So imagine a regular algebraic type graph. You have an x-axis, right? You have a y-axis up and down. But then there is, in three-dimensional space, a z-axis that runs straight through that graph. And so one of these p orbitals is taking that shape, and I drew it out as best I could as if it was coming, in and out of the carbon there. All right, so how does this look? We get even more complicated when we have a sp hybridization situation with a triple bond. So again, I'm not going to run through all of this, but I have the sigma bonds here overlapping. So one of these three is a single bond. Same thing with the H's. We know why the H's can't be hybridized. But if you look at the triple bond, I still, just like in the double bond, I have these sets of pi electrons, right? So if you take a look, I've got this to this, and that also works right here to here, right? So above and below. But then also, if you imagine one set can go above and below, the other set could go around. Imagine it almost like it's orbiting the triple bond, right? And so I look back here, and if I follow this pathway right here, boom, right to here, okay? That's looking at the Z direction, and so I can also host electrons there, and those would come right here, out, follow this black line, boom, around to right here, okay? And so this is probably the most difficult one to visualize, but this is what's happening in a triple bond. You really have the electrons that could be found above and below in one set of p orbitals, and then sort of in front of and in back of another set of p orbitals. And then I still have my hybrids left for the single bonding purposes. Before we had ethene. This is a special triple bond that is, that is called acetylene. Where are we with this? I went back one. This is acetylene. Sometimes people have heard of this. This is a lot of times used as a fuel when you're welding or things like that. Okay, so there's a simple method to finding out hybridization. I wanted to bring this to your attention. This method is primarily used if you're dealing with groups in the 2N level of the periodic table. So oxygen, carbon, nitrogen, most of your organic compounds, okay? If you have d orbitals, you can start having d hybrids, sp2 hybrids, and then you have to alter this a little bit. But for organic chemistry, this will work just fine, okay? So here's what you do. You count the electron domains around an atom. And to clarify, most of you guys should have learned this in general chemistry, but to clarify, when we are dealing with the electron domains are classified as one of two things. Either a lone pair, so any lone pair I find around the atom of interest is an electron domain, and then any type of bond. Now that does not mean a single bond, and then a double bond counts as 2 electron domains. That means any type of bond. Single, double, or triple counts as 1 electron domain. So you can use the formula Sp(n)-1, where n is the number of electron domains. So let's run through these really quick, and you can see how this works. I'm going to look at the center atoms, okay? So look at this carbon here in the center. If I want to find its hybridization using the quick cheat method, what I can do is I can say, okay, this carbon here, I find a single bond here, that's 1 electron domain, a single bond here, that's 2, and the double bond counts as 3. I don't count it 2 times, it counts just as 1 electron domain, so that's 3 electron domains. If I have 3, sp3-1, that gives me sp2. This carbon would be sp2. Now if you step back and you think about that, that makes sense, because that carbon is involved in some sort of a double bond. So it has to leave a p orbital behind, and it can only hybridize 3 of its 4 orbitals. And that's what we get. This would be sp2. If I look at this carbon, I have 1, 2, 3, 4 single bonds. 4-1, sp3, right? And so this carbon is sp3. This is chloroform. If I take a look at ammonia, this one will confuse students a lot of times, right? I've got 1, 2, 3, and so a lot of people look at it and think, oh, maybe it's trigonal planar, maybe it's sp2. But don't forget that these electrons here count as an electron domain, right? This lone pair. And so this is not trigonal planar. This is a tetrahedral electron geometry, and its molecular geometry is trigonal pyramidal, not trigonal planar. But when I'm taking a look at this nitrogen, I count this up as a 4th electron domain, and so I get 4-1 is 3. This is sp3 hybridized. That lone pair is actually sitting out in the hybrid orbital. And then finally, if I come to carbon dioxide right here, this carbon, I have 2 electron domains. The double bond here is 1. The other double bond over here is 2. And so when I take a look at those, right, I've got 2 electron domains, so 2-1 is just sp. And this carbon is involved in 2 sets of pi electrons, so it would need 2 p orbitals to remain behind. And that is correct. This carbon is sp hybridized. So a brief summary, sp2 and sp hybrids leave p orbitals behind for pi bonding, okay? Pi electrons are hosted exclusively in the p orbitals when we're dealing with carbons. And then Sp(n)-1 is a very quick cheat method for row 2 elements when I want to find their hybridization. So if you're on a test, you want to save some time, it's important to understand the theory behind this, but this is a sort of a quick and dirty way. And a lot of people also correlate it to, molecular geometry. So next lesson, we will be doing polarity and electronegativity and net dipole moments, a very important lesson. And other than that, thanks. Remember to like, comment, and subscribe if this was helpful. And this has been part of the Chem Complete presentation.